Hello, and welcome to this webinar, which is called How Computer-Aided Engineering Improves the Manufacturing Process of Nickel-Based Porous Electrodes. My name is Florin Muntean, and I'm a senior engineer at Elsyca. I'm specialized in surface finishing simulations and customer training for electrochemical process modeling. I'm holding a master's degree in automation from the Technical University of Cluj-Napoca. I have over 15 years of experience supporting industrial clients in applying simulations tools to optimize plating surface processes. Today, I'll be presenting our work in the context of NICKEFFECT EU project. The project's motivation is clear. As the demand for green energy solutions increases, so does the need for scalable and sustainable battery technologies. One key challenge is to replace platinum, a scarce and expensive material, with nickel, which is more abundant. Just to understand better how limited this resources is, I can tell you that all platinum ever mined would form a layer of just 37 centimeters thick on the bottom of an Olympic size pool, which is 50 by 25 meters. However, to match the electrochemical performance of platinum, nickel-based electrodes needs to have a higher surface area, and this is achieved by using porous microstructures. But we need to ensure uniform nickel deposition within that porous microstructures. So I will be introducing to you the plating process for nickel-based porous electrodes. Electroplating process can be a good option for providing the nickel-based layer of porous electrodes. Plating processes have the main advantage of not being limited to line of sight, as for example the physical vapor deposition method. Nevertheless, the drawing power of an electroplating bath has its limits, which are not only related to the depth in the porous structure that can be reached, but also impacts the uniformity of current density and deposit thickness. This is where simulation becomes a valuable tool. It allows us to analyze and optimize the electrodeposition process virtually, saving time and reducing the need for costly trial and error in the lab. In this webinar, I will guide you and explain the flow we used and how simulations were applied to optimize the manufacturing cell for such a porous microstructure. But before optimization, we need to make sure that the numerical model is the right one, so the first step was the validation of it. We started by simulating a small reactor using Elsyca plating master. Then we used those results as an input for a microscale simulation, and the results of that simulations were compared to measurements. So the first step was to validate the model which was being used in the laboratory. We have here a fabric, a carbon fiber cloth, which is 5 by 5 centimeters, this one, and which is kept in place by a holder, copper taped, and we have also 2 titanium anodes. The simulations were performed in Elsyca plating master. Now let me tell you a few words about Elsyca plating master. This tool is a plugin for SolidWorks and allows the user to leverage the CAD2Mesh solution to call Elsyca electrochemical solver. So as I said, it's an add-in which you can enable or disable in the add-ins list. Elsyca solver is based on the finite element method and can calculate electrolyte potential, electrode potential, current density, layer thickness, and alloy content. So this is the model trying to mimic the exact setup in the lab. And I will show you how to prepare and run a simulation in Elsyca Plating Master. So first we are creating the model. Then we need to define some groups which later on will be used to define connections and to better visualize the results. In order to speed up the things a bit, I already created the groups up front. So in this case, I have 4 groups, which in this case are anodes, 8 faces, XP fabric, which is the fabric itself, so only 2 faces, and we have XP cathode and frame. So this is the step where we defined the groups. The next step is to define the boundary conditions. Here the groups comes in hand, so we can select the anodes and we say this group, it's an electrode using the anode over potential. And here we can see the electrolyte being used, nickel wolfram or nickel tungsten, as you might know. And this is what we are using in this particular simulation. We also have this fabric that needs to be defined as a cathode, and there is a trick to mimic the behavior of the real carbon fiber. If we look at this model, we see here a flat surface. So it's kind of a 2D surface. But in reality, this fabric has a few layers on top of each other. So in order to mimic the behavior of such a layout, we use this option available in Elsyca Plating Master, which is called active fraction. So instead of using 1, so the surface is just what we see, we said this is 20 times bigger. And this will account for the 3D structure of the carbon fiber. We established this value performing a few iterations, and based on our findings, we decided that 20 is the most appropriate value for this case. Next step is to define the electrode system. So in this case, we'll have 2 electrodes. One is the anode, the other is the cathode. Also, there are a few contact points to be defined. So we define some contact points on the top of the holder in order to better mimic the real behavior of the model. Next step is to define external connections. So we have here a current generator, a grounding, and a few resistors to connect the contact points to the model. So while our model is set, the next step is to define the grid, the surface mesh. So first we start by defining the edge mesh and then face mesh. And let me show you how the mesh looks like. Also on the fabric, we use the finer mesh, so we get better results. By starting from the surface mesh, we can generate the volume mesh, the volume grid, and in Elsyca plating master, the volume grid is made out of tetras. So it starts from triangles from the surface and it's filling up the space, in this case the electrolyte space, with tetras. And now we can switch to solver settings, and we have a list of connection, and then we have process conditions. The process time is 480 seconds for this step, which is done in one shot, so we are not using time steps. And here we have a couple of settings for the solver itself. I'm not going to run the simulation, and I will just jump and show you the results. So this is another tool called Elsyca Explorer, and here we can visualize multiple scalars, one of them being the current density over the surface. We can see that the presence of these wing nuts has an impact over the distribution of current density. So the same results are here in the presentation. We did several trials, and now once we have these results, we switch to micro scale simulation, and we used another solver, electrochemical solver, to handle this. And again, we had a few sets of results which we compared to measurements. And the agreement was quite good. This validated our model and our approach to this type of simulations. Now, once the model was validated, the next step was to optimize a bigger reactor for a bigger piece of fabric. So if the first tank was only 10 liters, now we switch to a bigger tank, which is 120 liters. We have again two anodes in the model, one holder and a bigger cloth, which now it's 160 by 240 millimeters. And a holder around it, again, this holder, it's made of two parts, keeping the cloth in between as a sandwich. We started by using 8 small wing nuts on the side. In theory, this should be enough to keep everything in place. And we performed a simulation. Again, we used Elsyca Plating Master to prepare and run the simulation. This is a model which is even more complex, and the sequence of steps is exactly the same as for the small reactor, so I'm not going to show you again what the steps are. I will just show you the results. So based on simulations, we got some results where we can see the distribution of the current density. The aim in this case, it's first we see what is the distribution, and second we optimize this distribution because we want to have a uniform distribution as much as possible. This big cloth is going to be cut in smaller pieces, like 6 pieces, and the aim is that all of them have more or less the same properties, the same amount of nickel deposited in the microfiber structure. So this is where we started from, and then we had a few iterations, and we ended up with a more advanced configuration for this setup. And one was to replace the wing nuts from the corners with bigger wing nuts, and we added them on both sides, and using smaller ones in the center of this holder. And also we added some anode shields for covering this titanium mixed metal oxide anodes, and this improved the distribution of the deposit, and what we see here is the current density. In conclusion, for this model, we had an average imposed macroscopic current density of 570 amps per square meter over the cloth. For the first configuration, this one, we had a standard deviation of 74 amps per square meters. And then for the optimized one, this one, we had a standard deviation over the cloth of 56 amps per square meter. The onboard current frame, which is copper taped, is already largely reducing the spread. But what we did, we further improved it by adding these wing nuts, bigger ones, acting as the current rubbers. And by doing that, we were able to get a more uniform distribution over the surface of cloth. As you can see, by just using simulations, the user can compute upfront different scenarios and can try out different optimizations in order to get a better result. This approach can be used also in large industrial projects, and this is where our customers are using the software, trying to optimize, and not only trying but succeeding in optimize their processes. This was all for today. Thank you for your attention.